Hello, I'm Keyvan Parsan, along with Phillip Walker, will be presenting the paper by Policharla, Jupi, and Smith about complexity effective superscalar processors. Performance trade-off between the hardware complexity and the clock speed was analyzed. They proposed a complexity effective microarchitecture different from some modern ones that are being used. And that means it simultaneously achieves a high instruction per cycle rate while still permitting designs with high clock frequency, and complexity is measured in the paper and is defined as the delay of the critical path through a piece of logic and the longest critical path through any of the pipeline stages, which is determining the clock cycle. Some sources of complexity I looked at were sources that contribute to the complexity of pipeline architectures, and a model was created with the understanding that it couldn't possibly encompass all microarchitectures, but they did acknowledge the fact that this model applies to most modern superscalar processors. So this is the model that was created. Here we can see what they're referencing. That's a pretty common model that applies to most modern superscalar processors. Some processors that fit this model are the MIPS R10000, the MIPS DEC 21264, and we went ahead and listed some processors that do not fit this model, which is the Intel Pentium Pro, the HP PA8000, and the HL Spark 64. So for the methodology of the experiments in this research paper, the researchers selected a CMOS circuit to represent the pipeline structure. They based their design on designs from other microprocessor vendors, and some circuit tricks were employed to optimize the critical paths. For phase 2, the design was implemented and they optimized it for speed. They used a software known as HSpice to simulate the circuit, and optimizations were applied, such as manually sizing the transistors to improve the overall delay. Logic optimizations were applied to reduce input requirements, and the critical path was shortened by modifying transistor ordering. Wire parasitics were added in the model of the circuit, which was computed by calculating the length of the wires using the overall values of R metal and C metal, which are perspective, resistance, and parasitic capacitance in the metal wires per unit length, using the sizes 0.8, 0.35, and 0.18 micrometers. So moving on, they did analysis of the overall delay in terms of the microarchitectural parameters, looking at the issue width and window size, and what we'll be seeing from here on out are the simulation results from HSpice and what trends are identified in comparison with some of the earlier analysis. Some register rename logic that was used in this microarchitecture. Here we can see a map table that holds the current logical to physical mappings, then a dependence check logic. The dependence check logic detects dependencies and sets up the output muxes so appropriate physical register designators are selected. And because of this, the map table is updated at the end of every rename operation, and that is to be able to reflect the new mappings that come from this logic. And so this is like the first result that we see in terms of the delay coming from the register rename. And this shows how the rename logic varies with the issue width, meaning the number of instructions being renamed every cycle for the 3 technologies. And that is for 0.8, 0.35, and 0.18, which we can see in the figure. Total delay increases linearly with issue width for all of the technologies for 0.8, 0.35, and 0.18. And total delay as a function of issue width worsens as the feature size is reduced. For the wake-up, this is a diagram of the wake-up logic. Every time a result is produced, a tag associated with that result is broadcasted to all the instructions in the issue window. Each instruction compares the tag with its source operand. If there's a match, the 2 flags, which we can see in the figure, RDYL or RDYR, are set. And once all the instructions become available, the ready flag is set. Here's some more delay, and there's some delay analysis for that model. the delay of the window logic varies with window size and issue width for 0.18 micrometer technology. They also see in the figure we have 8-way, 4-way, and 2-way associativity being used, denoted by these different lines. And the results show that the delay increases by almost 34% going from 2-way to 4-way, and by 46% going from 4-way to 8-way for a window size of 64 instructions. So pretty significant difference. Here's some more SPICE results for the wake-up delay. We can see a difference from 52% going from 0.8 to 0.35 and to 65% as in total reduced from 0.8 to 0.18 micrometers. So still significantly different delay starting using the different sizes. Here's a selection logic from the research paper. So you can see structure for the selection logic is shown in this diagram, and the oldest first policy can be used. The leftmost, meaning the leftmost entries have priority. And so here are our delay results from SPICE for that for the wake-up logic. We can see the delay increases logarithmically with the window size, and we can see the different window sizes: 16, 32, 64, and 128 in the feature in the diagram. And the delay is less than 100% when the window size is increased from 16 instructions to 32 instructions. And here we see a structure for the bypass logic being used for this. It's a commonly used structure for bypass logic. And here we can observe that tri-state buffers are used to drive the result bits onto the operand wires from the result wires of the functional units. From here, Phillip will be taking the rest of the slides.
Hello, this is Phillip Walker, and I will now be discussing the rest of the paper. So starting with sections 4.4.2 about delay analysis. So the paper analyzed the length of delay for 4-way and 8-way processors, specifically analyzed the bypass delays that these two types of processors occur. And the delay of the bypass logic was largely determined by the amount of time it takes for the driver at the output of each functional unit to drive the result value on the corresponding result wire. And so considering the result wires as distributed RC lines, the delay is given by the below equation, where C is capacitance, R is resistance, and L is length. And this component of the delay is likely to become less significant as feature size is reduced, meaning that this function or this component of delay is predicted by the paper and by the authors to become less important and less of something to worry about as time progresses. So next, we see it also summarizes delay results and considers the implications of them further. It notes the problem of designing a future generation architecture with a faster clock cycle. It notices this because of the issues that it stated previously in the paper. It mainly specifies that window logic and the bypasses seem to pose the largest problems for delay as the clock cycle gets faster, and both of these cause difficulties if they're to be divided into more pipeline segments, so there has to be other ways of managing them. As you can see on table 2, it is overall delay results that they ran their studies on. So this would then, the paper then concludes that there exists a problem in how to design a future generation microarchitecture that has a faster clock cycle. So considering the pipeline shown in figure 10, add and sub cannot be executed consecutively because the result of select has to be fed to wake up. So as such, select and wake up can be considered atomic operations, and they must be accomplished in a single cycle. One solution for this is to include only a proper subset of bypass paths and take a penalty for those that are not present. Another is to use multiple copies of the register file, and this is referred to as a cluster in the paper, and the paper primarily focuses on clustering as the solution to this issue. So moving on to the next major section of the paper, section 5, complexity effective microarchitecture, the paper then shifts its focus into proposing a microarchitecture that would mitigate these issues that it discusses in the beginning. So based off analysis shown in the previous sections, the paper proposes a dependence-based microarchitecture. This dependence-based microarchitecture replaces the issue window with a simpler structure that facilitates a faster clock. And additionally, the paper notes that its proposed microarchitecture lends itself to clustering and mitigates the bypass problem altogether. So the idea behind the microarchitecture is to exploit the dependencies amongst instructions. As previously noted and as known, dependent instructions cannot be executed in parallel. So in Figure 11 is an example of how this microarchitecture would look. The issue window is replaced by a small number of first in, first out buffers. And the steering of dependent instructions to FIFO buffers is performed at runtime. So as you can see in Figure 11, the order is fetch, decode, rename, wake up, register, read, execute, access, and then write back. So because they use the FIFO buffers, there's a lot of ways that these instructions are then steered at runtime into these FIFO buffers and using these FIFO buffers. So let I with serif be the instruction under consideration. The following cases are possible. Case number 1 is all of the operands of I are residing in the register file, and in this case I is steered to a new FIFO acquired from a pool of free FIFOs. Case 2 is I requires a single outstanding operand to be produced by instruction I source residing in FIFO FA. In this case, there is no instruction behind I source in FA, and I is then steered to FA, else I is steered to a new FIFO. And then case number 3 is that I requires 2 outstanding operands to be produced by instructions I left and I right, residing in FIFOs FA and FB respectively. And in this case, you apply the above. And if the resulting FIFO is not suitable, then apply the same heuristic to the right operand, and it will be. So Figure 12, as you can see on the right, is an instruction steering example, kind of showing how the FIFO buffers would be used depending on what case they fall under. So the experimenters then compared the performance of their proposed dependence-based architecture versus a typical architecture with an issue window, and the timing simulator that they used was a modified version of the simulator simple scalar, and the specific baseline model is shown to the left in Table 3. So in Figure 13 is a graph showing the two performances of each, showing the performances of each of the two architectures proposed. The lighter gray is the baseline, the typical, the regular, and the darker gray is the dependence-based one that they proposed. Each benchmark that is listed of the 7 is from the Spec 95 suite and was ran using 500 million instructions. And as you can see, the maximum, as was noted, the maximum degradation is 8% in the case of the LI benchmark. Otherwise, the proposed architecture was nearly as effective as the typical one, but was still slightly less effective in all cases. Then the paper continues to discuss complexity and ways that the microarchitecture they're proposing can be more useful and helpful. They start to discuss the delay of wake-up and selection logic. They noted that both delays listed in the table to the right are shorter than those in the standard window-based microarchitecture. So they state that issue with 4 and issue with 8 The total delays in picoseconds are still much shorter than in a typical microarchitecture. From this, the paper concluded that by reducing window logic delay significantly, the proposed microarchitecture can be clocked faster than a typical one, which would imply that the dependence-based microarchitecture would be better in the future than the typical superscalar architecture that is being used now that they're comparing themselves to. So they then note that the real advantage of their proposed architecture is when it comes to building machines with issue widths greater than 4. This is where the clustering that they stated they were going to discuss more in depth later on comes in, because they then state that when it comes to crafting an 8-way machine, that has an issue width of 8 or more, all that they have to do is just use a cluster of multiple 4-way machines. So for example, they discuss specifically an 8-way machine using a cluster of 2 4-way machines as shown in figure 14. And this has advantages such as simplified wake-up and selection logic, frequent usage of bypasses, and improved access time of the register file. And so then the experimenters in the paper compare the performance in IPC for the cluster, the 2 times 4-way cluster, against the typical 8-way with a 64 entry window. They used the same benchmarks listed earlier in Spec 95, and as previously, the typical outperformed their proposed, but their proposed had similar performance in almost every case. It is notable though that for M88 KSIM and compressed, the degradation is close to 12% and 9% respectively. So continuing off of this performance test, however, because they noted that their proposed microarchitecture facilitates a faster clock speed, they then stated that a fair comparison between their proposed and the typical must take clock speed into account. And seeing the equation here, they note their proposed architecture supports a clock that is 25% faster than that of the typical one. The paper also then explored other designs of clustered architectures that interested them. The figure to the right shows 2 such designs. Figure A illustrates a microarchitecture where instructions reside in a central waiting window and instructions are assigned to clusters as they begin execution. This is referred to as a single window execution driven architecture. And figure B illustrates a microarchitecture where each cluster is a flexible window instead of FIFOs, and instructions are assigned to clusters when they are dispatched. This is referred to by them as a 2-window dispatch-driven architecture. They also discussed another architecture referred to as a 2-window random steering, where it is very similar to figure B. However, the instructions are just pure random steered to one of the clusters. And each window has 32 entries of the ones just discussed. So they then run more performance tests using the same Spec 95 benchmarks as previously. And a top graph shows the performance of the discussed microarchitectures, and the bottom shows the frequency of intercluster communication. Once again, the typical, the standard window-based one performs the best. However, the overall degradation is not nearly as notably bad for the ones that they proposed as one would expect, especially when they are optimistic about how theirs will perform in the future in comparison to the typical. Overall, the graphs show that cluster microarchitectures using distributed windows, when coupled with dispatch-driven steering, can deliver similar performance to that of an ideal microarchitecture with a large window and uniform single bypasses. This would lead them to believe that in the future, when it comes to supporting faster clock cycles, their proposed microarchitecture would be significantly better in the future than for the typical superscalar architecture that gets used now. So in conclusion, the paper studied the variation of delays of key structures in a generic superscalar processor with two important parameters, issue width and window size. And the results showed the logic associated with the issue window are going to become critical as future designs employ wider issue widths. And additionally, the paper then proposed a microarchitecture that is complexity effective, and this microarchitecture is referred to as a dependence-based microarchitecture, and it groups dependent instructions and helps to mitigate this problem. And here are our references. This is the paper. Thank you.